How
Hello,
about
Jacob.
you're planning this weekend?
I'm gonna go
Oh.
see my family.
See my family. You
Yeah,
you,
he's
you,
going
you go Tennessee.
Tennessee.
Yes.
Wow, good, perfect. We have to.
हाम्रो पुऱ्याइदिन्छ नाचभिडियो भन्नु न तिम्रो नाम के हो
Learn, teach him more.
Maranam Jacob.
Wow, that's the perfect.
सन्चै छेउ
Are you
सन्चै
fine?
छौ सन्चै छौ
That's Sunshine Show.
Sanjay Chao means,
How are you?
are you fine?
Sunshine Show.
Yeah.
Sunshine Show.
Yeah.
Alright. Sunshine Show.
छौ
Teach him one word, not a phrase, whole phrase.
Oh no, that's fine. What's good?
सन्चै छौ
It's good. I am good.
Yeah, but
मलाई ठिक छ.
what's good in Nepal?
Let's go to Nepal.
No, what's good and like
What's good?
That's good.
yeah. But no, like what is the like the word good?
Good.
Yeah, so
Ramro.
like
राम्रो
Ramro,
राम्रो छ
Ranro,
Ramro.
Ramro.
Yeah.
Sanchi Chan,
सन्चै छौ
Sanchi Cho, Ramro,
Ramro.
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 Oh, Ramro. Ramro.
मेरो you read मेरो as MMERW. Simply मेरो.
तिम्रो नाम
One day,
के हो?
within I think up to next semester you will be perfect in application.
Yeah.
Slowly.
You will understand what we talk about you.
Yeah, you have the great memory power.
Yeah, you have great memory power.
Sanchi
You
Cho.
pronounce words so clearly.
Ramro.
Yeah.
Ramro means it's good.
Ramro.
जस्तै wow, तिम्रो नाम के हो? You say मेरो नाम Jacob हो. And I will say wow, धेरै राम्रो नाम, good name.
Sanchi Cho Chandra.
म सन्चै छु.
What's that?
I'm fine.
सन्चै छौ चन्द्र भन्न जाने
Wow, perfect.
Yeah. You are doing better day by day.
We learn English
Like this.
like this.
Like this way. We have learned. And
But we have learned in later also.
yeah.
One day I will teach
Oh,
the
Kokara.
alphabet. Nepalese
Like
alphabet.
ABC. Like
There are-
ABC, there will be 36 alphabet in Nepali language. In English language, there are 26 A, B, C, D, J.
And we have
What we say? O, I, E.
12 vowel letters.
O, I, E. There are vowel letters.
Yeah.
Wow. Cool.
Like A, E, I, O, U. Oh,
You-
he's working on physics.
Oh no. I made a mistake in my integral, so
Yeah.
no, I'm cleaning it up.
It's a plane wave equation.
Yeah.
Yeah, it's too messy for me. I write this long.
Yeah. So
I did this way.
How?
I'm really hoping mine's not wrong.
I'm
either.
calculating 1 and 2 are.
Yeah, I know.
So I just didn't.
That's what we
write
did.
the final
Yeah,
numbers.
yeah, that's we already did it
Yeah,
like that
yeah.
way. So
We already did this, but like we
yeah.
we
So
I didn't write it down.
I made it only two
You
mistakes.
did 4 year series of at Modex.
Yeah.
Yeah, and you got the answer.
Yeah. Yeah.
Wow, good, perfect.
One page. This one.
Cool.
Yeah, nice handwriting.
You're very kind.
Hi.
Hello.
Hi,
No.
how are you?
How are you?
You left
Not
early in the yeah.
Not good.
Not good.
Why you left
No.
early?
Why?
I study for
Yeah.
exam and we together, right?
Yeah.
And same question.
Yeah.
Yeah.
He
So-
forget all things.
You forgot all things.
Yeah, I don't know why.
What happened for you?
Maybe because I have problem with my family and
Okay.
maybe I don't know why.
Yeah.
I study in my home more.
Yeah.
But here, forget all things. When I bet in my hand here, I remember for
Your family.
same dream. Yeah. When I went right,
Yeah.
all think. I don't know why.
Question was easy. You have
All
practiced too
think, all
much
think,
time.
study, yeah, all think.
Yeah.
Same.
Now you can do. Now you can do it. In the exam time, you forgot all.
I don't know why.
Yeah. It's terrible.
I don't know why.
You live with your family here?
My family know here.
No.
My country, yeah.
You live alone?
I'm alone, yeah. And I have now.
Hello.
Hello.
Hey.
Hey.
Yeah, I have some problem with my husband. And I don't separate. But I don't know why. Or problem with why I study. I don't know.
We just all need to study together more every week.
Yeah. I
yeah.
think, yeah.
That's the only way.
She studied while she was well prepared for this exam, but in the exam time, in the
Yeah.
exam period, she forgot all the things due to our family problem. That will happen
Yeah, that's what I'm
My
doing on
mom
the first
told
exam.
me, partner,
in your first exam.
That's what I felt like. But you know, I didn't study as
focus on
Study.
yeah, no focus on
Yeah.
your problem. Okay, mom, okay.
You have to. You do homework?
Yeah. Same.
I messed up my integral, so I'm rewriting it. I was like looking at it, I was like,
I have my
that's not the answer. And I was like, everything after this line is wrong.
Oh, the homework.
Yeah.
I didn't even. Yeah.
Oh god.
The question
Yeah.
was
Oh,
easy.
yeah.
I was looking, I was like, alright, let me try to
Me,
do this. I'm like,
afford.
wait. What about the pies?
For
Pi
all
cubed in
three
there, that
classes,
shouldn't be
yeah.
there.
Just
For
she
the
changes
second part
the
for the second part it's difficult, but
I got rid of
first
it
was
now.
fine.
You're so close.
Nothing
I
to
know.
do, just to calculate fx.
Why do I have to read?
Okay. The email is for this. How many questions you attend?
Oh, it's not correct.
just pull down.
There is a time you attend all
Maybe,
the
maybe,
questions.
maybe. I don't know, but
We have to do question before coming here, before coming to exam. Practice 3, 4, 5
I
times.
study more. And I remember all things. But when exam, when I look in the paper, I forget all things. When I put in my hand table, I remember all things. I didn't know why. Maybe because I have problems. Yeah, maybe. My mom told me with the shit. How my don't think about anything. Listen.
Yeah. So you remember how we did number 1 on homework 6 together?
Alright.
Yeah.
I never
Was
wrote
it
it
like-
down. And like when I did
Oh,
write it
class
down,
one.
I wrote a factor wrong, so
अब को तपाईको ठ्याक्कै
I got down to the part where you
एक
started
घण्टा
doing
15
integrals,
मिनेट सबै
and I drew an arrow, and I will read to you word for word
कहाँ हुनुहुन्छ तपाई
what I put on there.
Oh my god.
यहाँ
I can't believe I did this.
रेको घाम पानी
I said, full disclosure, I didn't want to do the integrals again, and I lost the first time that I did it. So I used a computational resource this time.
तपाईँ ल्याबमा हिँड्नु
So I just drew the integrals and then did an arrow as to what they end up being.
I can't bring myself to do
अनि
that.
ल्याब जानु
I'm like stubborn, you know.
हुन्छ ल्याब
Yeah, I'm stubborn too, but on the computer side of things.
Yeah.
How are you doing? Not feeling alright? Not feeling too well?
Oh, I was exposed to some on Monday, so I'm just being extra cautious.
I appreciate your cautions.
Yeah.
You're so close. Why did you stop?
Oh, because it's not going up. It makes me feel bad because I got it right the first time, like on whiteboard, but
When it really counts.
it's frustrating. Yeah.
You can say it like, oh, I can't do this on paper. Can I just use the whiteboard?
Yeah, no, yeah. Can I see a picture of it? Yeah. There you go.
The next lecture.
This is a group effort.
Maybe. No, our next lecture.
next lecture
It's a
Because I
reference.
think, no.
Yeah, yeah.
Oh my God.
next lecture show
Thank you. Alright, everybody's good now. I've graded only some paper, 50% of the papers. Finish up tonight. Next class you will get that. The test papers. Good. I think most people found it easy from the last one, it looks like. At least it looked like that.
yeah it looks like easier
That's what I mean. Out of my grade, it looks like people have done better than the first test. It looked like.
I think I'm doing better than last test I think I have done better than last test in this test I have
That's why I study with group, I study more, but when I class, I forget all things. I don't know why. Maybe. I study with group and weekend and I stay in my home more, but when I look for this, I forget all things. When I got in my hand whatever, I remember same thing. But when I write all things, forget all even how. Yeah, that's hard. I don't know why. I cannot judge that or what happens.
She studied with us and she was
Yeah, I
okay
know.
at the time, but in the exam, she said,
Yeah, I mean, you have to, try, a few things. I mean, I thought we had done many things, partially different. We did it in the beginning of the class, we repeated it, except I changed the geometry from, horizontal, vertical. So, I want to know whether you can apply boundary conditions correctly. That was the only thing I was testing, right? And, because it was decaying the y direction rather than,
The thing that threw me off, and I could just be that I did it wrong or something, was the fact that you had a sinusoidal boundary condition.
I just wanted, because it can be a varying function, right?
Yeah, but that would, it destroyed in the summation for the.
That's okay, there's only one contribution.
Yeah, and so, okay. I did that and I was like.
Yeah, I mean, it was, in fact, you didn't even have to do the Fourier transform because it was so obvious, T naught sine x equal to, I mean, the only one thing, there was only one possibility, was not all the BNs contributing, only one of them contributed. It was still, a simple thing, just to, in principle, it need not be constant, right? I mean, that's the only way I can satisfy that boundary conditions of 0 and pi, or whatever it is, right? So, it was, the coefficient in that case was even simpler than usual. You didn't have to, you can just guess it in some sense, So,
and that orthogonality relation in homework set, I made a mistake in homework set as well, like that Laguerre differential equation.
yeah, because I wanted you to guess, I don't want you to even do the full, that's the whole purpose of Sturm Liouville, right?
Yeah.
You don't have to go through the generating function, all these formula, you don't have to, at least normalization you have to do, but at least orthogonality.
Yeah.
In some cases you have this factor, weight factor, right? I mean, why you have that weight factor, in some cases you don't have a weight factor, right? That keeps coming in quantum mechanics, that's why, I mean, some, special function you have the weight factor, sometimes you don't have it. And you know where it is coming from.
The example, that was Bessel function.
Some people wrote it as Legendre. I don't know why. Even though weight factor was correct, it was with Legendre.
It was because I sat there and I needed to, in my mind I had so many things going on, and sometimes my wife says that I put the stupid and stupid smart sometimes, where I was looking at it and I was doing everything else at least I feel like I was doing correctly, but then for some reason I was like, I don't remember the symbol for Bessel, even though it's clearly not P, and I went, Bessel is P, right? And I just put P, thinking that it stood for Bessel, and I literally was like, sitting at my desk at home later that night, and I was like, why did I put P? It was, I don't know, I just for some reason looked at Bessel and said, the symbol for that is P, for sure.
Right, yeah. I thought, I didn't give any of the special function because I thought we have done at least only Legendre and Bessel in full depth. That's why I gave that. I thought you would, And for Legendre, we don't, in fact, Legendre, we don't have a factor because it is a Sturm Liouville already.
No, I fully
fact,
thought it was Bessel. I just for some reason read it in my mind as Pessel, not Bessel, Hessel or something.
I was not expecting the questions in that list, and I was expecting you would give one question from derivative method.
I know that derivative method would kill the time, right? We also, and I found that derivative method, when even the homework, most people got it incorrectly because, because
in the generalization part, I have.
Because sometimes it looks complicated. You have to go back and put the you have to take the derivative with strict sigma, and most of the terms will become 0 when you put the initial root. It will be sigma equals 0 something in this case. It looks complicated, but you have to do the derivative. Almost everything disappears, and that was the case. So I realized that if I gave the derivative method, then half the time you also have tested a little bit, right? I mean, you know how to apply Frobenius series and all that. And so I said that it looks more repetition, and also it takes time. Then I cannot test the other things, which are new things you have to learn also, right? So others are not coming or what? I mean, okay, Ishwaranga is not here. He's coming?
get started with Fourier transforms today. All right. So what we did last time was, if a function is periodic, okay, and satisfies some Dirichlet conditions, right? We could, let's, I'm going to, right now I'm going to call f of t. The function has a periodicity big T. We could write it like exponential of I t and going from minus infinity to plus infinity. These are complex okay, this is what we did. It's a combination sine and cosine. If it is real coefficient, and we know that this complex coefficient could be written in terms of an and bn's, right? An plus ibn over 2 or something like that. So this is what, we'll start from this. Okay, so here the function is periodic, then we know I can write it like this. Okay, so I'm just starting from what we had done last time. All right, so Fourier transform is written. It's a function. It's a representation for a function which is not periodic. So we start with this and then we'll go from here. So that's the representation that we want to give. We are knowing this, okay? And which is not periodic and satisfies the following condition. F of x. I'm going to call it here f of x. Okay. This should be fine. So we're giving a representation for a function f of x, which is not periodic, and satisfies that the integral of square modulus of the function, integrate over the entire domain, infinite domain, is finite. Okay. This is like, we had Dirichlet condition for for Fourier series. For Fourier transform, this condition has to be satisfied. When we give Laplace transform, that condition will not be satisfied. We have to come up with a different representation for a function. Okay, so we slowly go from periodic to non-periodic function. So this is what we are going to do. So what do we do here? So this is what we have learned so far. I have to represent for a non-periodic function. So what do we mean by knowing this? Here, the C of n is what? The coefficient Cn is nothing but 1 over the periodicity of the function times that. Okay, so let me write down this clearly because I need space also. So this is for periodic functions. this is what we know. And that is Fourier series, complex Fourier series. Right. So, knowing this, we need to get a representation of Fourier transform. So what is the first thing that we can do? If a function is not periodic, what does it tell you about t? What can I? So this is the function is periodic t here, right? So if a function is not periodic, I just want to get, from knowing what we know, I want to guess this representation for a Fourier transform, right? So what can we say about the periodicity of the function?
It's periodic over infinity.
Yes, t is infinity. I mean, it is not repeating itself, so t is infinity. Okay, so that's the first thing. So can we let t go to infinity in these expressions? Okay, so that's the first step. All right, let's just here. Let's first. I'll do that, but let's. If I substituted Cn in this expression, what do I get? I have 1 over t. All I've done is substitute for Cn here, right? And I'll let t go to infinity in this expression. But before that, we have to observe many things. Let us call this function. I'm going to call this variable almost like angular frequency because this is time. So I'm going to call that as omega n, okay? N here is discrete, right? So omega n plus 1 would be 2 pi t, which is discrete, it is this. Right. So delta omega n is nothing but 2 pi over t. Right? So what I'm going to start doing is 1 over t is nothing but delta omega n over 2 pi. I'm going to start substituting that. So I'm going to write f of t to be the following. 1 over t is delta omega n over 2 pi. You can do that. F of t prime exponential of minus I omega n t prime dt prime, and then exponential of plus I omega n t. Okay, so all I've done is substitute for this as omega n. Why have I done this? As t tends to infinity, so we know this is something that I have to do for the functions not periodic. Okay. Now, when t tends to infinity, what does it say? These frequencies are not discrete, they will become continuous. The spectrum will become continuous. That is one thing. Okay. So, because the delta omega n is defined by this, So the spacing between omega n's is, becomes closer and closer. It tends to 0, it's continuous, the spectrum. The frequency spectrum becomes continuous. As t tends to infinity. So we can replace, what does that mean? That means I can replace delta omega n by d omega. Okay? It's a continuous variable. Okay? So I can do the following. So t tends to infinity, so this can become negative infinity, that becomes plus infinity, and this will become continuous spectrum. So I can write this as minus infinity to plus infinity, t omega over t 2 pi, minus infinity to plus infinity, f of t prime. Now, I will call this as a continuous spectrum, so omega dt prime, exponential of I omega t. Is all right? Can you do all these things? All I've done is now, because this is not discrete, I can convert the summation into integration. Okay, that's the first step. And I can convert this negative t to minus infinity because t is infinity. And this is now a continuous variable, not a discrete variable. I can make it as omega. So this quantity here which is a function of omega because you integrate over t prime, is what is called as Fourier transform. Okay? And normally written in this notation, and this whole thing is called as Fourier inversion theorem. Okay? Let me write down this. So if a function is not periodic, I could write f of t as, so this is the equivalent of the complex Fourier series now, is nothing but, I've observed 2 pi, I'll just explain that also a little bit more clearly, but that's also important. Negative infinity to plus infinity of f tilde omega, which is a Fourier transform, okay, times exponential of I omega t d omega. Tilde omega is nothing but 1 over 2 pi negative infinity to plus infinity of f of t prime. That's the variable, w variable, so dt. You can always get f of t from here if you knew f tilde is just exponential of f tilde omega exponent I omega t dt. Okay, it's already done. Okay. So one thing which I want to tell you is this definition that we've written, this normalization factor is a little bit arbitrary, right? I could have I have just absorbed it here, but I could have distributed equally when I have to go back from one space to other, t space, omega space. In some books they will put equally. 1 over square root of 2 pi here, 1 over square root of 2 pi here. You know, there's nothing in this definition I could have done it that way. There's nothing holding me. So if you find in the definition of, in some books, 1 over square root of 2 pi, it's because then you have to be consistent when you're going back and forth between one space to other space. You know, if you're done here, then it is 1 here, it's 2 pi here. If you put 1 over square root of 2 pi here, put it as 1 over square root of 2 pi, because all of them is coming from this definition only, right? So I could have written it like this. Nobody's stopping me from writing like that, right? So, but within your own definition in a given problem, be consistent. Otherwise, you'll have a mistake of this square root of 2 pi, right? And so let me first do it with this definition, and then later on we'll try to do it symmetrically, so that I don't have to remember where I have to put 2 pi, where I have to put a value, ×1 or something like that. Okay, so is this clear? Okay, so it's nothing coming directly from here. So all we have put is t going to infinity and made the spectrum continuous. That's all we have done. I want to get the definition of Dirac delta function from here, so I erased this expression, so I want to get it. What I wrote was f of t, and from the complex series, what we had is the following. But properly so that, let me go back. We wrote. Right, let me, yeah, it's important. Okay. This is how I had written, right? Minus infinity to plus infinity, d omega over 2 pi. This is what we had before. I'm just going back to that. Minus omega d prime, okay, dt prime. And then I had a d omega here, I think. I did that. Exponential of pi omega t. Okay, so this is what I have. So let's try to do something here. So, supposing I change the order of integration. Here, t prime is getting integrated first and then the omega, right? There's nothing stopping us from changing the order of integration. Okay. So if I change, I did the omega integration first, okay, and then the t integration. So this is the expression we had when I substituted, we converted the Fourier series to Fourier transform. And then I identified previously this quantity within this as, f tilde omega. That's what I have done. And the rest as, I wrote it like that. So this is the expression we had before we wrote these two. I'm going back to that expression, and I'm trying to give you the Dirac delta functions, integral representation for this. So what does this tell you? I mean, if your left-hand side have to be ft, what does it tell you about this expression? What should this be? What? I mean, give me the variable. Delta of t minus t prime, right? Because that's the only way I can. So that's what gives me the definition of Dirac delta function. T minus t prime should be nothing but 1 over 2 pi negative infinity to plus infinity exponential pi omega t minus t prime. So what does it, physically, what does it mean? This one, t minus t prime is sharply peaked at t equal to t prime, right? It's infinity at t equal to t prime. Everywhere else, it is equal to 0, right? So that is that. And how is it being composed? I mean, that is left-hand side, that's a property of Dirac delta function. It says exponential I, what is? It is combination sine and cosine, right? It's harmonic waves. Okay, sine omega and cosine omega. It is superposition of harmonic waves in infinite range, omega, all frequencies, right? And they have the same amplitude, these harmonic waves of different, frequencies that they combine, and they have to be in phase at t equal to t0 for it to be infinity. Other rest of it is, the phases are not in phase, they cancel, and that it becomes 0. So that is the physical meaning of this, why we have it, right? I mean, it is really superposition of harmonic waves of all frequencies, because omega is going from minus infinity to plus infinity. So it's like summation, you can think of that, like, superposition of harmonic waves of all frequencies and of the same amplitude, because the amplitude is 1 in this case, of all this case. And they have to be in phase at t equal to t prime for it to be sharply peaked at as a function. So at t equal to t prime, they have to be in phase. Okay, that's the physical meaning of that. All right. So that's where, if you see the integral representation of Dirac delta function, that's where it comes from. Okay, so you always see that in quantum mechanics. So let me write down this. So in Fourier transform all the time, you juggle between the integration and somehow get delta function, then the integration becomes simpler, right? So that's what it is. Okay. The other important property of Dirac delta, which we'll understand through not Dirac, Fourier transform in general, is the function may behave in one way in one space, okay, t space, let's say, or it can be x space. The conjugate space is the p space, if you have x and p. So t and omega here. So if it is spread out in one space, let's say omega space in this case, because it's a superposition of sine and this thing, and then in the other space, which is a t space, it will be sharply peaked. Okay, so that's a dual property that we come across in quantum mechanics all the time, right? I mean, and that's also one of the reasons you want to go into a different Fourier space to make your life easy in terms of whatever integration or whatever you're trying to do, the work, because the whole thing viewed in a different space will be easier. Okay, so you always go between real space representation and k-space or momentum space representation. Right? All right, so let us go and check this a little bit more also. So I have a distribution. which has a value 1. Okay. So, and I want to get the inverse transform of this function and see what happens to it. Okay. So f tilde omega, this is a function that we have. It is constant in this, let me call it minus omega plus omega, all right, regime. And it is 0 elsewhere, okay, everywhere else it's 0. It is constant between minus omega and plus omega. What's the Fourier transform of such a function? The inverse transform of such a function. I'll just put it omega, let's call it inverse transform of that function. I want to get f of t, of the corresponding to this function. I'm also going to start implementing equal distribution, let's say, so that, because most of the time that's how it's written. The normalization factor equal.
Shouldn't it then be for f of t, it's the integral from negative small omega to bigger omega of 1 e I omega t?
Yeah, because minus infinity, the other location is 0, right? So I could write it as f of t as 1 over square root of 2 pi. Negative omega to plus omega. The function is 1, right? F tilde omega is 1. So I have exponential of I, omega t. This is f tilde omega. Yeah, okay, d omega. Alright? Because it's 0 elsewhere. Minus infinity in other location is 0. So I can write it like that. Function is 1. Okay. So this gives me simple elements at this point. Nothing but exponential of I omega t over it, because integration is over omega, right? Minus omega plus omega. So I have, it looks f of t looks like exponential of I omega t minus exponential of negative I omega t over it So what is that function?
So this is where the consistency of where you're putting the constant matters, because you defined it as f squiggle of omega, and you're assuming that that has the other half of the square root of 2 pi.
Right, I started with this definition, right? I mean, where did I, right, I'm starting with this definition, right? I mean, yeah. So, yes.
Is that 2 sine omega t?
2 cosine theta plus I sine theta, right? So 2 and I will cancel, right? 2 sine omega t over t we have, right? And I have a square root of 2 pi also here, okay? Now, I'm going to write this function as, maybe I can write a square root of 2 over, okay, let it be like that, square root of 2 over 5, right? And then Now I'm going to multiply and divide by omega here. Let me just and keep the 2 pi. Okay. All I've done is, added, multiplied, and divided by omega. Now we have this function. What is the behavior of this function? This is how f tilde omega, in the omega space the function behaves. What's the behavior of this function? What do we know about sine omega t or omega t? Sine x or x? So I want you to plot f of t as a function of p. Sine x over x, and x tends to 0 is what? 1, right? So at t equal to 0, the peak is, it is peaking, actually that's when it is. So we have a function which is oscillating like that. It's nothing, okay, this 0 is here, that what the peak is. And the peak is, the value of peak is 2 omega over square root of pi. Alright, and it is 0 at first will be t equal to pi over omega sine pi, right? So this is, I think, pi over omega. You will have the first 0 and all that. Okay. Now, this is the function. Now, if I make this distribution, I consider a finite, it's, has a value 1 between minus omega and plus omega. Supposing this is constant everywhere, right? What happens? This distribution is uniform everywhere. If I let omega tend to infinity, what happens? So this is what we have, okay? Now I'm going to say, let omega go to infinity. So I have uniform distribution everywhere in space, okay? It's constant everywhere in omega space. So I want to see how it looks in the t space. So what happens to the peak?
Towards 0?
What? The peak? No, what happens to the amplitude of the peak? Omega tends to infinity, right? The width of the distribution is not 2 omega, it is now. It's everywhere. So I'm just making omega go to infinity. So it becomes sharper and sharper, and that one, comes nearer. So it tends to Dirac delta function. So this is what I'm trying. A uniform distribution in one space, in the dual space, which will be the t space in this case, will be sharply peaked. That is a Fourier transform property, right? One space behaves, function behaves one way. It is it's spread out. In the other space, it is localized, strongly localized. Okay. So that's what I want you to understand. And this gives me another representation for the delta function too. That's what I want you may come across that. This is the most common form, but in most books, another form will be given. I would like you to recognize that form also, okay? So as omega tends to infinity, this becomes really, this function, limit omega tending to infinity, this function becomes Dirac delta function. All right, now since so basically what I want to tell you, because I had 1 over 2 pi in my Dirac delta function before, so what I have is really, I should write root 2 pi Dirac delta function should be 1 over, so this is the quantity which is equivalent to, because I had 1 over 2 pi in the original definition, the way I wrote, should be equal to 2 omega limit omega tending to infinity of that function, 2 omega over, I can cancel now omega, okay, but I needed that initially to look at that, so I can cancel the omega, so it's okay at this point. Is nothing but, I'll keep that also limit 2 over, I can cancel that easily, 2 over that sine of omega t over t, okay, and so the Dirac delta function under representation that I can give is as follows. When I bring that is 2 over pi, so it's nothing but limit omega t sine of omega t over pi. Pi t squared. This is also representation of Dirac delta function in addition to that. Okay, so. So if you come across this representation, you know where it is coming from. You know, you consider the uniform distribution, okay, and in one space, and then you try to look at take the Fourier transform of that, then you get this representation. So you need to, you know, it comes, different representations are there, but these are most common ones. So I want you to recognize these two representations of Dirac delta function. I would like you to recognize them if it comes in quantum mechanics. All right. Okay, so you already said a function which is sharply peaked in one space will be will be flat in the other space. It has, okay, that's a dual property of going from one space to other. T and omega are dual spaces that I already mentioned. Okay, now. I'm going to write Dirac delta function as 1 over 2 pi of minus infinity to plus infinity I omega t omega. I can write it like that, right? So what is this function? Delta of minus t. What is it? What is delta star of t? What is it? And what can we say about the relationship between delta t, delta minus t, and delta of delta star t? That's complex conjugate. Okay? So can I say delta of minus t is this? I say delta star of t is same as delta of minus t? I can say that. Can I say delta star of t is equal to delta t?
Because it's only 1 at 0.
That's the reason. So what I'm trying to say is, you may say, okay, this cannot be true, I mean, because it's got minus, minus and plus. No. Delta function, you know the property at t equal to 0, it has to be 0. So because of that, so you may see in books where sometimes, you know, the function is written I omega t definition, sometimes minus, but they have the same because of the property of Dirac delta function. So, you know, because these things keep on flipping in the Dirac delta function, you'll say sometimes the plus I omega minus omega, but it is the same at t because of the way it is, right? They're really the same. Okay, so I could write my Dirac delta function also as this. Okay. So if you get confused, what is this? Should I put plus or minus? You don't have to worry because you have to see. Okay, I mean, so that's because of you know, the property of Dirac delta function. Okay? So they are identical. So I just want to mention that because that's another thing you may come across. And all right, what is the Fourier transform of the Dirac delta function?
Is the Dirac delta function still? Like, is it not?
What's the value? In the other space is a dual space. Delta t is sharply peaked at t space. I mean, the way, you know. So I wanted the Fourier transform that is in the dual space. And you have the definition there for Fourier transform for any function, whether Dirac delta function or whatever it is, it's just there.
With 1?
Right, we have to, you know, if you just plug in blindly, it looks like square root of 2 pi, 1 over square root of 2 pi, right? Because if I just use this definition, because this is, I think your book, I think is incorrect. It writes 1 over square root 2 pi, because here what are we trying, direct delta function, right? I mean, minus infinity to plus infinity of, this is how your book is writing, okay, and gives this as, if this is of course 1, right? I mean, it is, this is existing only for t prime equal to 0, so the whole thing is 1. So your book is giving this as this, okay, as a Fourier transform there. But I think it's 1 because we have already, you understand, we have taken the 1 over 2 pi. It's constant, whatever it is, it's constant everywhere, and in the other space, it is sharply peaked, okay? So I think they have made a mistake because the definition in the Dirac, we absorbed in the function 1 over 2 pi, it should be 1, okay? They just blindly use the definition and then put it as 1 over square root of 2 pi. It should be just constant, which is just a value of 1, which we know from here too, right? We have done it that way too. If it's 1 constant everywhere, it is Dirac delta function. So, but I wanted to also emphasize on the normalization factor, that how we absorb is up to the user, right, where we are distributing. And since we put 2 pi in the function everywhere in the Fourier, in the other space, the factor is 1, that definition, right, rather than equally distributing like that. We have to go back to this definition rather than this definition. Okay. So just be careful on this. Okay, all right.
Would you expand the Dirac delta function by doing it in an integration?
What do you mean by that?
Let's say instead of having the math needing a single point of it being 1, like that function right there, we're not 1 at a single point, we're 1 between negative omega and positive omega. Is there a way to express that in a Dirac delta function?
It is not, it's minus infinity to plus infinity. Eventually, minus omega to plus omega, it is that function, right? But we put limit omega tending to infinity, so you have to be careful that
well I'm not asking about this in particular, I'm asking in general. If I said I needed to have something be 1 over something to only exist from A to B, mathematically, could I do that by having an integration of Dirac delta functions?
Sure, yeah, that's sure. That's what, property of Dirac delta function. You introduce that, or remove, exactly, sure. So actually, when you do in quantum mechanics scattering theory and all, you will be all the time juggling, exploit the property of Dirac delta function to solve many of the integrals, double integrals, and all of that. Basically, the order of integration, all these things will be flipped, so that you can somehow recognize Dirac delta function and the integration becomes simple, right? And you're always looking for a term like this. Okay. It is dt, let's say. Depending on what you're doing, omega space, whatever it is. You're always, if you have several things, you always, can you get an integral like this, right? And there may be other things, right, in your integral, but can you do that? Then you know that part of it is delta of t minus t prime. And you can then simplify the rest of the integral. So you're always looking for this kind of a term in double integration, multiple integrations are there, and so you can reduce a double integration to a single integration because of that delta function.
As long as or along with the e to the negative I omega and e to the plus I omega.
Yeah.
Yeah.
Both. I mean, because we know the diagram doesn't care whether it's plus or minus. Yeah. Okay, let me just talk about other things which we came across. in Fourier series. So we also have Fourier sine transforms, okay, and cosine transforms. So if a function is odd, then we know that f of negative t should be negative of f of t. This we know, this is a property. If you have such a function, then instead of the Fourier transform, you can write Fourier's sine transform. I'm putting S to represent sine transform. Function is odd. Then the Fourier sine transform is, I give the formula and then we prove that. It's given by square root of 2 over pi, so the normalization factor is different. And then instead of negative infinity to plus infinity, you have 0 to infinity, okay? And then f of t sine omega t dt. Alright? So if f of t is even, then the Fourier cosine, this C stands for cosine transform, okay? So this is a cosine transform. Fourier cosine transform. Is given by, so first the integration limit has changed from instead of minus infinity to plus infinity, it is 0 to infinity, and the normalization also has changed. So again, these things in scattering theory and quantum mechanics, you will, they'll use this quite often. Okay, so let us go, let's try to prove this. I mean, I'll prove only this. This you can maybe take as a homework, but try to understand. So this is the definition of the function. We know the definition of Fourier transform in general. I put it in symmetric fashion, okay? The normalization are symmetrically distributed between function and the Fourier transform. And so similarly it will be here, symmetrically, it will be nice form you get. Okay, if this is the function, all I'm just saying is function is odd. So f of t is negative f of t prime, right? So if this function is odd, what can we write this term as? F tilde omega will become what? If f of t is odd, is not a function, what is f tilde omega for such a function, which is the Fourier sine transform, but what will it become? What can I write it as? F of t is odd. And exponential, can I write it as cosine and sine? Which one is the word? Ft cosine omega t prime dt prime is not a function, right? So integral to minus infinity, that will be 0. Okay, so the only thing which is going to survive here is all I've done is written omega t plus I sine omega t. Okay, so it's this term which is the second term which is survive. Okay. With the minus sign, so I have a minus I negative infinity to plus infinity f of t prime I sine omega t prime, integration is over dt prime. Okay, so I get a function. I get that. Alright. So this is odd. So that is odd. So what can I write that integral as? Can I write it as 2 times 0 to infinity? So I can write this as negative 2i over square root of 2 pi as 0 to infinity f of t prime sine of omega t prime dt prime. Right? Which is nothing but negative I square root of 2 pi. Right? Still not the same. What I have to prove is that. So I got this negative I sitting here. Okay. It's not quite the same as that. All right. What can I say about f tilde of negative omega? If it is odd in the t space, in the conjugate space, which is omega space, is it still odd? Also f tilde omega. Okay, so the function is, if it's odd in the real space, in the one space, it's also odd in the other space. Okay, that's something to keep in mind, and that's what is going to help us get into the next step. Actually, what I need to do is what f of. All right, I need to prove that, right? Okay, let me just. Okay, what can I do for f of t prime? What is f of t prime?
Would that be negative f of negative t prime?
Okay, we can go back here, right? I mean, f of t definition is there, right? I mean, for us, f of t is still that. I mean, I need to apply all that, right? I mean, so f of t, can I write it as f of t? Can I write it as t prime at this point, right? I mean, 0 to infinity. Still here at this point, this is where the other property will come in. I think 1 over root 2 pi, okay, minus infinity to plus infinity of f to the omega, okay, and it's like Russian doll in this Fourier transform. Keep on, omega t prime, okay, d omega. Okay, so I substitute for that, okay, and then I have sine of omega t prime dt prime. all I've done is substitute for that, okay, from that definition, okay, and I have sine omega t prime still here. Now since f tilde omega is also an odd function, right, I can write this as 2 times 0 to infinity, okay, so that I can do. Okay, that is one thing, or I can substitute already, I got that, right? Okay, let me first make that as 2 times 0 to infinity. That I can do because it's a odd function, and I will have only what here, sine omega t, right? Also. So what happens to this? Let's see. I need to get rid of this. I need to get this definition, right? F of t sine omega t. Yeah, I need to let me. If I did this, what happens? I get it. Double integration. That's not what I wanted. I think I just. So f of t is in this definition for a okay, I know what it is going to be now, is also 0 to infinity of f tilde omega sine of omega t d omega. Okay. Integration over omega. We have this expression also. Okay, it's just inverse of that. If I, okay, now I have this. I need to prove this actually. Right? So all I know is f of t is that right now. I can that we know it's an odd function. Okay? That's a definition I know because I still cannot, because I have to prove I cannot apply that yet. So let's see, f of t is 1 over square root of 2 pi. It's an odd function, so I can put 2 times 0 to infinity of, oh yeah, pi plus, okay, no, sine, this is sine of omega t, d omega. Okay. It's a plus here because of the sine, yeah. This I can write from that definition because that is still, because what I want to say is f tilde omega is also an odd function that we have to recognize, okay, first, which we know ft is odd, f tilde omega is also an odd function. Okay, if you recognize that, then I have this as f tilde omega cosine plus I sine, right? So I have a plus sign here. So this is where I think I can now go back, either one of the two, plug it in. Okay, yeah, I got it, okay. So what I want to write is f tilde omega is then square root of 2 over pi, okay, that will become I square, that will become minus plus, okay, that will be fine. So I have 2 over pi, okay, that's what we have. And what I'm trying to do is get this guy going inside 0 to infinity of f tilde omega sine omega t prime d omega. So what I've done is now substitute for this, okay, ft prime, and this has an integration too, right? It is over omega, so this is 0 to infinity integration over omega, and then I have another integration which is over t prime. sine of omega t prime dt prime. Okay, let me just explain this now. All I've done is got an expression for f of t, recognizing that is an odd function. So you get that. And I'm plugging this function into that. Okay. So I have two integration. One is over omega, and other is over t prime. So let us now recognize basically now we have f tilde omega is nothing but so what is that? Sine omega, that I have. So I'm going to call, this is nothing but f of t, right? I mean, so if you recognize this as f of t, then f of t in this case is 2 over square root of 2 over pi. Recognize that as sine of omega d prime f tilde omega d omega. Okay, this is f of t prime, if you want to call that. Then we have this guy is square root of 2 over pi 0 to infinity of f of t prime. Okay, sine of omega d prime dt. Okay, so both are now, this is the sine transform, the sine inverse transform, if you want to call it. Okay, this part of it is not the full inverse transform, it is the inverse Fourier sine transform. Okay, so you have to recognize that as that. Both have an S in it. So it is the same way we did for Fourier transform. It was inside each other, right? I mean, so this times what happened? One more thing, Jack, is sine of f tilde omega. This is what I'm writing. For each one, it goes the other way around. If you have f tilde sine omega is square root of 2 over pi, this quantity, okay, and it's the other way around. Okay, so which is all buried in this definition of substitute back again. So that's where you get the, I cannot stop at this stage because I have this negative sign, so I still have to understand what's going on. So all I have to go back and get back to the definition of this. And here I'm recognizing this thing is an odd function too. Okay, so I'm going to have only the sine term here with a plus sign. Okay, this time is with a plus sign, right? Cosine plus sine, so you have plus 2i, the same, and then substitute back into that, and you're examining what it looks like. Okay, so basically, what you have to know is if the function is odd, you end up with a very simple expression. Okay, so just integration limit is 0 to infinity, function f of t sine omega t instead of exponential of I omega t. Okay, that's what it is. And the normalization factor is not 1 over square root of 2 pi, but is square root of 2 over pi. Okay, so we are writing again like f of t. The way we wrote the f of t definition was, we had two things, right? I mean, when we went to a complex series, when we did it, we had we had this, right? This was also an integral, right? I mean, so it was, that's how we got it. So similarly, it is an integral within an integral, okay? I mean, so that's what is happening with the sine transform also. You have this, the double integral. One is over omega, the other one is over t prime. Okay, this is over t prime. So this quantity is one of them. So this times, if you want to call this f of t prime, sine omega t prime t prime. So that's what that is. And again, we are distributing this constant equally, right? We are distributing here in one of them, in the other one. Square root of 2 over pi is distributed equally. Previously, 1 over 2 pi was distributed equally. Now we are distributing square root of 2 over pi equally. We have this. Now you can put that in one of them here, and we have in the other one also square root of 2 pi. Square root is over everything. Okay. So this is one term over d omega, which we call as f of s t prime. want this is not just a sine subscript of it. And then multiply by sine omega t dt. So they are very symmetrical. That's not hypertendency. Okay. So you can go back from the t space to omega space, just as we did in this, or even for odd function you can do that, except now you don't have to worry about it is exponent plus I or minus r. Here it was flipping, right? The sign was flipping, right? In the Fourier transform it's negative, in the inverse Fourier transform it's plus. So the advantage of here is both of them are sign, you don't have to worry about. And whereas cosine, it is, similar thing except it's cosine function. So it's much simpler actually. Once you recognize function is symmetric, this confusion is not there. Where should I put negative exponential? Okay, here it is very fixed, right? I mean, unlike delta function, here it is in the inverse Fourier in the Fourier transform negative. This is inverse of that function, positive. Whereas in the sine, if the function is odd, you don't have to worry about it. It is very simple expression. That is the simplification you're getting out of this. Okay. How much time do I have? We are out. Okay. Give me 1 second. I want to make a comment about, because that's the most important, interesting one. If you take the Fourier transform, as I said, if something is uniformly spread in one space, it's sharply picked. The only exception is the Gaussian function, Gaussian packets, right? The Fourier transform of a Gaussian is a Gaussian both in the X space and T space, okay? Or in, whatever reciprocal dual spaces, both are the same, except the broadening has changed, okay? It is in one case it may be a little bit more broader, maybe a little bit, but the functional form is exactly the same. And that has very important consequence in quantum mechanics, because that's what leads to Heisenberg uncertainty principle, actually. The fact that Gaussian packet does not change its shape. Unless, unlike the other one, right? So that you can do by Fourier transform again, but that's the only exception. Except, the width of the function, let me write the function expression here. I'm not going to prove this to you, but okay, this is a Gaussian function, right? If you remember it from your StatMech class or statistics class, this is a Gaussian centered at x equal to mu, right? Whereas in this case, Gaussian is centered at t equal to 0. I have a Gaussian function packet, and the width of this distribution is tau, okay, in the t space, f of t versus t. The only difference which happens when you take the Fourier transform is the following. When you take the Fourier transform of the function, it becomes 1 over square root of 2 pi exponential of minus half tau square omega square. So what is happening is this tau, which is in the denominator, is now in the numerator. That's your, in the Gaussian, that's the width. This is your width, right? The standard deviation, that is your sigma. So that is here in this case, which is like mu is, take that as 0, that's what's happening here, t, right? It's looking like that, except tau square is your width. Now in other space, what's happening is the shape of the curve is the same, except it may be broader, okay? And the width is 1 over tau. So the distribution in the time space is delta t is 1 over is tau. the distribution, standard deviation in the other space of this function is 1 over tau. The fact that delta t times delta tau is 1, okay, is what's sort of implication of this Gaussian distribution does not change shape, has implication is at the heart of your Heisenberg uncertainty principle actually. There's no proof of Heisenberg uncertainty principle, but this is sort of the one which sort of indicates about Heisenberg uncertainty principle. The fact that a Gaussian wave packet does not change the Gaussian nature of the wave packet is at the heart and the core of your quantum mechanics in Heisenberg uncertainty principle. Okay, so that is coming from Fourier transform theory. So most of the Fourier transform stuff comes in some locations in quantum mechanics. So just having some idea is good. Because you will see them again and again. And in foundations of quantum mechanics, maybe the fact that Gaussian wave packet does not change its shape may come, and that's because when you transform this, the function form doesn't change, except that width has become the standard deviation, which is in the denominator, goes up, and because of that, the distribution that of this function is different. It is 1 over tau. In one case, it's tau. In the other case, and the error in the two spaces, is basically approximately 1. Okay, so that's sort of has implications. All right, let me stop here. Yeah, so basically you always have to look for delta function when you have, infinite integrations. Once it comes, you can recognize that form, either changing the order of integration, then you can calculate the double integral or multiple integration, multiple integrals for there, you can simplify the problem. Okay, so that's the advantage of the whole thing. So you have to know, even if you don't remember anything, just remember the integral representation of the Dirac delta function. That's the most important thing, okay, because it will come again and again in quantum mechanics.
Thank you.
Yeah.
Certainly answers no. Just reading my test, and it's pit available. Can I grab it before then? Or
I have not entered it yet, but you've done well. Except for that. I knew I had get everything and then gave it to you.
I just wrote the wrong letter. It was brain dead,
Yeah, I have not entered in my grade book, that's why. Yeah.
I have homework. I completed too. My integral when I was finding the Fourier coefficient, it turned into a mess.
Did you put it correctly, the displacement, the other one, it's like slope is changing, right?
Yeah.
So you have to use the correct slope equation for that, the plugging. Right, that's the only complicated stuff I think, yeah.
Okay.
Yeah.
Well,
Yeah, and there's also I think Fourier coefficient is a bit more messy than
Yeah.
usually.
could I turn it tomorrow morning?
No problem, no problem.
Okay. Yeah. Because
Mhm.
like we're all like in one of the study rooms and we worked it out and we were like, all right, this came out perfect. All right, now let's study for the test and let's go forth.
Mhm.
And then I never wrote it up.
Mhm.
and now going back through, I'm like, oh no, why do I have a pi cubed in there? Uh-oh, I took a factor of that out and I put it back in.
Mhm.
Yeah.
Yeah, I just wanted you to try it a little bit before the test so that you could
Yeah,
talk a little bit
yeah.
for your series. Yeah, that's the only reason I did that. I said, I know you didn't have much time to do it, but
Oh well.
I thought, going through the Fourier series,
It was.